Black holes are likely the strangest, most exotic, and most misunderstood things in the universe. They're often depicted as these infinitely dark and terrifying behemoths that devour everything in their path. But they also inspire the greatest stories of time travel, wormholes, and alternate dimensions. One of the things that makes them so fascinating is their unobservable nature. They do not emit any kind of radiation we can detect, which makes them notoriously difficult to study. One of the only ways physicists can get to know more about them is by looking at how they influence their environment. In this video, I'm going to explain what we do know about black holes, I'll talk about the many mysteries that still surround them, and I want to debunk some of the common misconceptions about these fascinating objects. Let's begin with probably the most important question. What is a black hole? It's definitely not a hole in the classical sense of the word. It's an easy mistake to make since these kinds of depictions of black holes showing how they curve spacetime in a much greater way than planets or stars do make them look like holes, but they are much more like objects or points in space rather than holes. The term black hole is a bit inaccurate. The idea of a body so massive nothing could escape from it was first proposed by astronomer John Mitchell in 1784, and he referred to this object as a dark star. Later in the early 20th century, this idea of a dark star was starting to get taken seriously as a possibility thanks to Einstein's theory of general relativity, and was then referred to as a gravitationally collapsed object. The term black hole became more popular in the 1960s and quickly caught on for both scientists and the general public. So, if not a hole, what is a black hole really? The simplest way to put it is that it's a collapsed star. Stars have a life cycle. They are born when a cloud of gas and dust in space becomes big enough that gravity starts to pull the cloud into itself. When the pressure and temperature inside get high enough, nuclear fusion of hydrogen atoms into helium atoms starts to happen, which releases huge amounts of energy, and the star begins to shine. Remember, gravity is the main character here. Gravity makes that things with mass or energy are pulled towards each other and is one of the fundamental forces in our universe. The energy released by the nuclear fusion happening inside the star is enough to withstand the force of gravity pulling the star's mass into itself, and it nicely balances out into a ball of plasma that can shine for many billions of years, until it runs out of hydrogen to fuse into helium. The ultimate fate of a star depends on its mass. A smaller star like our Sun will go through a red giant phase. It will swell up as it runs out of hydrogen. The internal pressure from nuclear fusion energy pushing outward can no longer balance against the inward pull of gravity, and the star will eject its outer layers into space, forming a spectacular nebula. The remaining core is now a dense stellar remnant we call a white dwarf. The heaviest stars become supergiants and die in an extremely violent and energetic explosion called a supernova. Most of the star's material gets ejected into space where it can then form new stars, but the star's core undergoes gravitational collapse. This can result in a neutron star, an incredibly small and dense stellar remnant that spins very quickly, sometimes 600 times per second. If the mass of the stellar remnant is high enough, starting from about 3 to 4 times the mass of our Sun, the strong gravity of the object will cause it to keep collapsing forever. No known mechanism is powerful enough to stop the implosion, and so the result is a black hole, an object so massive and compact that nothing can escape its immense gravitational forces that distort space-time itself. Black holes can grow by eating other things in space, usually stars and cosmic gas and dust that gets too close, and it's believed that this is the way black holes become supermassive. Sometimes two black holes come close to each other and end up merging, making one bigger black hole. However, this doesn't explain some of the very largest supermassive black holes we know of. They're just so big they can't have been formed by a typical dying star. Maybe they grew after a collision of two galaxies with black holes at their center, and those galaxies merged again with other galaxies. So the black holes could eat a lot of stuff, but it's not clear if supermassive black holes could have grown that huge in the time since the Big Bang, about 13.7 billion years. Finding out how these objects came to be is still an active field of research in astronomy and physics. Now, this doesn't mean black holes are these monstrosities that devour everything in their path. If you replace the sun with a black hole of the same mass, not that much would change. Since the center of mass everything in the solar system revolves around stays the same, all the planets would just keep on orbiting it like always. Nothing would get sucked in unless it got too close. This also means that black holes at the centers of galaxies are not slowly eating their galaxy. Their gravitational influence is big, but not big enough that they could pull in all the billions of stars contained in a galaxy. So, a stellar core many times more massive than our sun collapsed into something so dense that nothing can escape from it seems terrifying. But most black holes just sort of sit there quietly. The force of gravity is determined by an object's mass, after all. Black holes are not that different than any other object in space, whether it's a star or planet. Because Earth's mass is so much greater than a human's mass, it feels like we're stuck to the ground. Earth's gravity pulls us in. But if you get far away enough from Earth, its gravity can't pull you back anymore. You got away from its gravitational influence. It's the same with black holes. You won't get pulled to it as long as you stay at a safe distance. But you're going to have to keep a much greater distance than you would from a small planet like Earth in order not to fall towards it. Scientists were able to prove there is a supermassive black hole at the center of the Milky Way by looking at how the stars orbiting the center of our galaxy were behaving. They're not getting sucked into anything, but they do have unusual orbits around this invisible center of mass, the black hole. As a matter of fact, this black hole eats only about 1% of the cosmic material that gets pulled around it. Turns out, black holes are kinda terrible at eating things. Just to illustrate how compact black holes are, if hypothetically speaking the Earth turned into a black hole, it would be less than an inch across. You could fit it in your pocket. Well, technically you couldn't because this thing would contain all of Earth's mass, so it would weigh about 6,000 billion trillion kilograms. Okay, so then what happens to anything that gets too close to a black hole? Things get pretty intense. An object like a star would quite literally get stretched apart or spaghettified by the extreme gravitational forces. The material forms a ring called an accretion disk. It spins around rapidly and is superheated to millions of degrees, effectively making black holes some of the brightest objects in the universe. Which is ironic given the name black hole. Over time, some of this material does fall into the black hole and is lost forever. But because of the fast rotation of the accretion disk, most of it gets ejected back into space. These massive bursts of energy are another way scientists can detect a black hole. The accretion disk is what we actually see in these pictures of black holes, taken by the Event Horizon Telescope collaboration. The black hole itself is hiding inside the dark shadow at the center. Now, in case you're wondering, if we can take pictures of black holes, why did I say we have to find them by looking at how they influence their environment? You see, to get these black holes pictured, it's a bit more complicated than pointing a big telescope at a point in the sky and boom, black hole. First of all, you have to know a black hole is there in the first place, before you can decide to try and image it. Now, the consensus is that there is a black hole residing at the center of pretty much every galaxy. Scientists looked at the galaxy Messier 87, an absolute behemoth located about 54 million light-years away in the constellation of Virgo. It contains several trillion stars and is one of the largest and most massive galaxies in the local universe. It's about 500,000 light-years across and one of the brightest radio wave sources in the sky. At the heart of M87 sits a supermassive black hole with a mass billions of times that of the Sun. The image we have of it was made using data from the Event Horizon Telescope, which is actually 8 big radio telescopes in a trench coat. Basically, these 8 telescopes work together to form one giant Earth-sized telescope. With the data this project gathered from looking at the core of M87, scientists were able to patch together this image of the black hole. In the same way, we now also have a picture of the supermassive black hole at the center of our Milky Way galaxy. The reason these pictures look blurry is because the light coming from the accretion disks of these black holes had to travel enormous distances, not just through empty space, but through the stars and gas and dust of the galaxies themselves. So it got quite distorted. Even with highly sophisticated computer modeling, these aren't perfect images, but it's still impressive. Now we also have pretty accurate simulations and artwork of what the accretion disk looks like. Just so you know, images like these where the black hole appears like this black sphere with a flat disk of superheated material surrounding it aren't really accurate because gravity will distort the image of the accretion disk. This is why this rendering in the science fiction movie Interstellar is often considered a great example of what a black hole would look like up close, but not too close. Photons normally travel in straight lines, but strong gravity can bend their paths, causing an effect we call gravitational lensing. And so you get this halo of light, which is made up of several images of the accretion disk as photons get warped by the extreme gravitational forces. In this rendering of a black hole without an accretion disk, you can spot the same image of a star several times, and the closer to the black hole you get, the more you see the same images coming back, but they get more and more twisted, until you get to the black hole's event horizon and light can no longer escape. Gravitational lensing can also be spotted around giant clusters of galaxies. The amount of mass they contain is so huge, the light of galaxies behind these clusters gets bent and distorted. I did say strong gravity can also disrupt space-time. So how does that work? Could you travel time by venturing close to a black hole? As a matter of fact, you could travel forward in time. Just as gravity bends space around massive objects, it also slows down time, since time and space are one and the same thing, and so space-time sort of gets stretched out. This is an effect called time dilation. Time runs slower the closer to a black hole you get. This happens with all objects with a lot of mass. Your clock will run ever so slightly slower on the ground than at the top of a tall tower, because the Earth itself has an effect on space-time because of its mass. It's just that the effect is much greater near an object with enormous mass, like a black hole. In the movie Interstellar, the characters visit a planet that orbits so close to a black hole that they experience time dilation. While they spend only a few hours on the planet, many years pass for their colleague that stayed behind on their spaceship. To be fair, while time dilation is a real thing and the writers of Interstellar relied heavily on real physics, a planet orbiting a supermassive black hole is probably highly unlikely. If the time dilation would be as significant as it is in the movie, the planet would be orbiting really close to the black hole, and the tidal forces the planet would experience would be so huge it would get ripped apart fairly quickly. Aside from that, it would also get blasted with high energy radiation from the accretion disk. At that close distance, the planet would probably already be in the process of falling into the hole anyway. Lastly, landing on this planet and then leaving again would be extremely difficult to do because of the immense gravitational forces. The closer you get to a black hole, the more speed you need to escape its pull. Now, a 2020 study suggests a planet orbiting a black hole would technically be possible, but under very specific circumstances. The black hole would have to be absolutely huge, at least 163 million times the mass of the Sun. For your reference, the supermassive black hole at the center of the Milky Way is only 4 million solar masses, and so it rips apart approaching things very quickly. In a much bigger black hole, you could technically have a planet orbited at a distance where the tidal forces are less severe. The black hole would also have to be spinning extremely quickly so the planet's orbit could be stable, and then there's still the issue of high energy radiation and other stuff being pulled into the black hole, possibly crashing into the planet, so it's pretty safe to say it would not be a nice place to visit, let alone settle. So yeah, Interstellar does get a lot of the physics right, but it's still a science fiction movie. It's a very good movie, it's probably my favorite, but it's fiction. Anyway, getting close to a black hole is not a terrific idea. Once you go past the event horizon, there's no going back. This is the black part of the black hole. Nothing can escape past here, so it's completely dark. The event horizon gets its name because of the fact that any events past this point can no longer be witnessed. The event horizon is not the edge of the black hole, however. It's not even really a thing, it's just a point of no return. Anything that goes past would need to travel faster than the speed of light to escape, and so it's just not possible to go back, because nothing in the universe can travel faster than the speed of light. The event horizon of supermassive black holes is at a much greater distance from the hole itself than it is with stellar mass black holes. You could still be 100 million miles away from the black hole, but already past the event horizon. If you and your friend were to hypothetically travel to a black hole and your friend goes near and past the event horizon, you would see them slow down and come to a complete stop before they ever seem to reach the event horizon. Then this still image of them would become redder and dimmer as gravity distorts the light coming from them. Your friend could light a torch or try to communicate with you via radio waves, but none of these signals would ever make it out and reach you. If you would both travel past the event horizon, you wouldn't be able to communicate either, since everything, no matter if it's things, particles, or waves, is always falling towards the black hole, no matter what direction it's traveling in, and you would be lost forever. In case of a smaller stellar mass black hole, it's likely your friend would get torn apart and spaghettified by gravitational forces before reaching the event horizon. With a supermassive black hole, you could possibly travel past the event horizon and not get spaghettified for quite some time. Assuming you can't be destroyed, what would happen inside a black hole? The short answer is nobody really knows for sure, and given our current understanding of physics, it seems that we will never find out either. In the universe, we get most of our information by looking at how light is emitted, reflected, blocked, or absorbed. Since black holes don't emit any light, any form of electromagnetic radiation, it's not possible to find out more about anything that goes past the event horizon. There are many hypotheses concerning what goes on inside a black hole, and they mathematically make sense going by how the physics of our universe seem to work. But in the end, we have no observational evidence, and we can't do any experiments to test these hypotheses to find out what the truth is. There are three options here, however. The black hole is a singularity. It's made up of a material we can't know anything about because it's hidden behind the event horizon. Or it's something else entirely. A singularity is a mathematical solution born from Einstein's theory of general relativity. This theory predicts that mass curves spacetime, and so if you do all the math involved, you get a singularity, an infinitely small point where all matter pulled into it is squished down until it's infinitely dense. Einstein himself didn't actually believe that black holes could exist, but by now we have found that they very much do exist. Another possible solution is that inside the event horizon, matter gets squeezed into a new exotic form of matter. Remember, the death of a star with enough mass will result in either a white dwarf, a neutron star, or a black hole, so we already have a few examples of how matter behaves under extreme gravity. As you probably know, all matter in the universe is made up of atoms. An atom consists of a nucleus made up of protons and neutrons, and this nucleus is surrounded by a cloud of electrons. In normal forms of matter like me or my phone, there is a lot of space between the nucleus and the electron cloud. If you were to scale the nucleus of an atom to the size of a basketball, the electrons would be about 3 kilometers away from it, and the rest is empty space. Atoms are so tiny we don't experience this empty space at all. Solid matter like your phone or yourself appears solid because the atoms are just packed together rather closely, even if the space between them is quite big at the atomic scale. Now, extreme gravity can squeeze matter down into itself so hard that it now consists only of protons with free-floating electrons between them, still resisting the forces of gravity. And this is what a white dwarf is made of. If you add more mass, and so gravity crushes down harder, the protons and electrons are forced together into neutrons, and so you get a neutron star, which is heavier but smaller than a white dwarf. If you add even more mass, the neutrons will no longer be able to resist the force of gravity, and the object will form an event horizon. So anything would need to travel faster than the speed of light to escape this barrier, which is, as you know, not possible. And so the stellar remnant could consist of some form of matter we can't know anything about because we can't observe it. The event horizon prevents us from doing so. And then there's all the hypotheses about time travel, including into the past. Wormholes that would allow for travel to the other end of the universe, wherever or whenever one chooses. Perhaps a traveler could end up being spit out by a white hole, the exact opposite of a black hole, where nothing can go in and matter is constantly pushed out of. Maybe someone could end up in an alternate universe this way, where the laws of physics are different. Or it might just lead to a hole in the fabric of a multiverse, where an infinite amount of universes float in an infinite ocean. An observer might cross the event horizon and see all of time pass them by in what feels like only seconds to them, before they are engulfed by the loneliest darkness, and no longer able to perceive anything. Or it could be something we can't even imagine. There's also the question of the further evolution of black holes. We know how they're born and that they can grow, but how will they end? What will happen to a black hole when there's no more stars and dust and other black holes to swallow? Will the universe end in immeasurable darkness, with most matter contained in black holes, lonely reminders of brighter times? Physicist Stephen Hawking proposed that black holes could evaporate due to quantum effects. Black holes could give off incredibly small amounts of radiation we currently can't measure, because this radiation would only be a billionth of a degree above absolute zero. And so a black hole could shrink over the course of an enormous amount of time. It would take so long that all stars and galaxies would have burned out, and in an infinitely far cold future, even black holes will succumb to the struggle against the increasing disorder our universe seems to be heading towards. But in the end, we don't really know, and unless we discover something entirely new and different about physics, we most likely never will. This is what scientists currently know about black holes, and while it sure is exciting to speculate and write down equations, as long as none of these hypotheses can realistically be tested, they will remain hypotheses. Even if the math gives us mind-blowing possibilities of what could happen when you take physics to the most extreme. But let's keep in mind our perception of the universe has changed many times over the course of history. We used to think the Earth was at the center of the cosmos, but scientists found out this was untrue. Then we had to change our ideas again after we figured out our galaxy was not the universe, but just one of many other galaxies, and that our universe is terrifyingly huge. There's no predicting what the next groundbreaking discovery might be. And so the search for the truth continues. Thank you for watching. I hope you learned something new today, and I will see you soon.